So population and investments are example of increasing exponential functions, and so important applications of decreasing exponential functions is radioactive decay. So we use pretty much the standard equation, y equals y0 e to the kt, except because the constant k is now a constant of decay rather than a constant of a rate of growth. There's a rate of decay, not a rate of growth. Therefore, we specify k as a positive number and then throw it into the equation with a negative sign in front of it. So you could easily, like, to me this is a little artificial. Why not say that the rate of growth is a negative number, and then you wouldn't need this negative sign here, and k would just be negative. But in many physics applications, and in particular in your textbook, chapter 6, page 352, defines the equation for radioactive decay this way. They say you have a positive number k, which is called the rate of decay, and then you put a negative in front of it in the equation. So essentially, the positive growth exponential functions are saying the more of something you have, the faster it grows. And so, those graphs look like this. The more I have, the more it grows, right? But then exponential decay is just I do a reflection around the x-axis. That's the effect of changing the sign of the independent variables. It gives you a reflection around, the y-axis. So then your growth looks like this. So this one says, the more I have, the faster it grows. This one ironically says, the less you have, the longer it lasts. All right, that's what exponential decay is really doing. And the things that do that typically are radioactive elements. So the more of the radioactive element you have, the faster it decays, and then the less there is, the slower it decays. It has to do with statistics. It's all very physicsy. All right, so that's the equation. Here, we also in these types of applications with radioactive decay, so we have lots of applications, whether it's dealing with radioactive waste or some how you carbon date things. Carbon dating all has to do with the radioactive decay equation. Same equation describes all those things. That's what's sort of amazing about mathematics generally. All right, in radioactive decay, we often talk about something called half-life. And so that's worth a brief discussion. Half-life means when do I have the y half, which is half of the amount I started with. And we want to know when that happens. That's called the half-life. So you can find the half-life as a function of what k is and vice versa. So this k and this half-life are related to each other. So it works like this. No matter what radioactive decay I'm talking about, or I could be talking about something that's not necessarily radiation, but I don't know what else decays exponentially besides radioactive things. Maybe sound energy, heat energy. I think heat energy. I think if you leave something on a table and it cools, I think that's an exponential, but I don't know. It's been too long since I studied that. Anyway, here's our equation, y0 equals e to the negative kt, right? So what I want to know is when that is equal to 1/2 of the y0 that I started with. And then so what's interesting about it is that you can cancel the y0s off, means that length of time that it takes to end up with half as much does not depend on how much you started with. Mathematically, that's because the y0s cancel. And then in terms of, that exponential decay function, it means that if I go from here to here, I go for, let's say this is the amount of time that decay takes me from like a certain amount to half as much, right? Well, no matter where I am, that same amount of time is going to take me from however much I have to half of that. My picture is not phenomenal, but that's sort of what's going on back there. All right, anyway, so to solve this, yeah, this looks good. So negative kt equals ln of 1/2. Something I've noticed is that because everybody knows now that the antiderivative of 1 over x is ln of absolute value of x, everybody wants to put ln of absolute value on everything, okay? This is not an antiderivative, so it's not ln of absolute value of 1/2. It's just ln of 1/2. All right, but you can do this tricky thing. Ln of 1/2 is equal to ln of 2 to the negative 1, right? And then you have this property of log says I can bring the exponent out the front equals negative ln of 2. So ln of 1/2 is just negative ln of 2. That simplifies this equation because the negative kt equals ln of 2 takes care of both the fraction and the negative signs. Kt equals ln 2. And then, so I could solve it either way, right? I could do k equals ln 2 over t, or I could solve it the other way and say that t equals ln 2 over k. So if I know the rate of decay, I can get the half-life. If I know the half-life, I can get the rate of decay, because they have that simple relationship. Okay, so here is an example of using that. So here's a true statement. Plutonium-239 has a half-life of 24,000 years. How do I know that? Because I looked it up on the internet, and that's why I know it's true. All right, plutonium-239 has a half-life of 24,000 years. So so plutonium, by the way, is only used for, as far as I know, only used for weapons. It's not used for nuclear reactors. So nuclear reactors use U-238, right? And then the byproducts are like there's a cesium one and a strontium one, and they have long half-lives, but nothing like this 24,000 years. They have like I don't know, so it's like 100 or something. Anyway, I just grabbed this example. Plutonium, we would only get that out of nuclear weapon. So if I'm taking 50 grams of plutonium-239 and I bury it in a toxic waste dump, okay, then probably I'm decommissioning nuclear weapons is what I'm doing. So so I'm making the world safe from nuclear weapons, but I'm creating a toxic waste dump. So am I doing good or bad? I don't know. It's kind of comes out in the wash. Anyway, the question is going to be how many kilograms are left after 200 years? All right, 200 years, that's longer than any of us are going to ever live. But how much of the plutonium is still going to be there? You want to take a guess? Okay, now let's work it out. So the first thing we do is we find k, so we can go into our equation, right? We want to use y equals y0 e to the kt. That's our standard exponential equation. Remember, none of this is calculus. It's just all algebra. The only calculus part is this equation came from this differential equation. That's the so in a AP exam question, they might give you this, and you just need to see that go, oh, I know that means this. And then I can, use my algebra skills from there. Now, of course, I've lost my page. Yes, okay. So I need to know that, I need to find the k here, right? All they gave me is the half-life, and if I want to use this equation, I need to find the k. So I will say k equals ln 2 over 24,000. And I did that on my calculator somewhere up here, or right there. And I got 2.8811 times 10 to the negative 5th power. And of course, I'm going to leave that in my calculator so I can use it. Again, exponential functions are very sensitive to error, so you want to make sure you include a lot of decimals when you do the calculation. As far as what I'm going to write, I'm just going to write 3 decimals. All right, then I can plug into my original equation. I can say y equals, my y0 is 50. Now I can say it's e to the k, which is 2.888 times 10 to the negative 5th. But I'm going to remember this positive number k. So we actually have a negative right there for exponential decay. So it's going to be negative here. I made that mistake when I worked this out before, and I ended up with more nuclear waste than I started with, and that's how I knew I had to go back and put the negative in. Anyway, here's our equation. All right, and then so I want to know after 200 years, so I'm just going to go y equals 50 e to the negative 2.888 times 10 to the negative 5th times 200. All right, and then I just throw that into my calculator, remembering to copy and paste the 2.88. That way I didn't have to like write out all those decimals and the exponent and everything. And here's what I got, 49.71. So now, this is really, if you want to do significant figures, there's one significant figure. So the answer is 50, one significant figure. After 200 years, nothing has happened, according to significant figures. Okay, but let's give it 3 decimals like AP exam would want. 49.712 kilograms. After 200 years, we haven't even lost half of a kilogram of material. And that's why plutonium is so dangerous, aside from it being classed as one of the most toxic substances known, since a single atom of plutonium in your lungs can give you a terminal cancer. Anyway, half-life. There you go. All right, now that's enough about exponential equations. Again, it's really just all algebra. So the only new thing is that instead of stating that it's an exponential equation, we can state that dy dt equals ky, and then you say, oh, I know that means y equals y0 e to the kt, and then you do all your algebra thingies from there. This is all this is really about. Okay, so you get some homework on that, which is from your book, chapter 6, page 357, 1, 2, 3, 4, 5 nifty problems to do. But we're not done with this, because next we're going to do logistic equations. And in the first video, I accidentally kept saying logarithmic, but it's logistic equations, which are a completely different thing. That is what is coming next.